This is the Summer Hall in Edinburgh, where they have the brilliant geometry exhibition on, which is partly the fault of Henry, who you may remember from other videos on my channel, and he's going to give me a tour around the exhibition. Room 1. This actually looks like an art gallery now.
Right.
So you've positioned things strategically around the room, which is nice. And this I recognise.
Yeah, so we did this on one of the other ones.
So, in my professional studio at home.
Right, on an ironing board, as I recall. Yeah, so this is, so there's a sphere here, and it's got these weird curves on them that somehow magically produce this perfectly regular
Right. So there's a single light here, there's like an LED.
Yes.
If I block that, I block the whole thing.
Yes.
And that is projecting what looks like an incredibly regular grid.
Yes, it took us forever.
I've got to give it to you, that is phenomenal.
Lined up.
Like normally down here it's a bit, you can kind of imagine it should be a perfect square, but you've nailed that.
Yeah.
So what did you do? Did you have to...
Yeah, so there's so many different degrees of freedom of moving this thing at do not touch, right? The rest of this thing is all wonderfully interactive. This one, we will kill you.
I would have gone with the bigger sign personally.
Yeah, because...
If the bigger sign just tipped the whole thing too far, yeah.
But what this is showing is that one of the big ideas is this stereographic projection, which is this kind of projection casting shadows from the sphere to the plane.
So by stereographic, not stereo, not as in like dual vision.
Not stereo as in stereo.
Stereo as in it's a sphere. And that
solid,
all of this is positioning that exactly at the North
pole. on the surface of the sphere.
Right.
So that the light rays
start on the surface and then hit every other possible.
They go inside, they go through, and they hit and that's this map.
I do like the fact that light is a perfect way to do lots and lots of...
It does it, right?
Light,
So Mercator projection, of course, right? Everybody's very familiar with the map of the Earth. Unfortunately, you can't. Map of the Earth. Right. So this is stereographic projection done to the globe, the actual globe,
which is a sphere.
Right.
Which is convenient.
And then you can
fiddle around. Oh, that's nice. So people are allowed to touch this one.
Oh yes.
Okay, cool.
But don't bounce it on the floor.
Wait, so I can put like Australia.
Yeah, go for it.
Look at that.
Yes.
It's heavier.
Unfortunately, the northern hemisphere is a bit heavy, so you need a bit of friction
both in terms of 3D printing and geopolitical.
Right, that's true.
And so
come on. There we go. Nice. There's Australia. Perfect.
Nice.
But
that's a map. Come on.
Right. And so this isn't a commonly used map for maps of the world. Well, partly because you got Australia here, but everything else is.
Is it because it ruins area? I guess.
Well, so does the Mercator projection. It's just sort of harder to get all of, it does in fact get everything, all of the world on the entire plane.
If you've got an infinitely large...
Well, yes, you do need a large piece of paper.
Which gets expensive.
But yeah, so stereographic projection, unlike the Mercator projection, you can do with just light. The Mercator projection, you can't just do it sort of
because you're unpeeling bits, whereas this, it's just a straight projection.
Actually, it's because it involves logs. We thought about it. It would be great to be able to have the Mercator projection done with just casting shadows, but it doesn't work.
Okay, and this is quite nice because people come into this room and they kind of get maps projecting a sphere to a surface, and this is just fun.
That's showing the
unexpected. Yeah. And then you've got hands-on.
Right.
Okay, so this is the next room, the House of Tiles.
This is the House of Tiles.
There you go. Right. And so what have we got in here?
So these are all triangle tilings.
Okay, so where are we going to start?
Right, let's start with this one.
There's a lot less space in this room.
Right,
that's okay.
Yes, it's, so this is called the 5-3-2 triangle tiling.
Yes.
So we got the tiling on the wall.
Yeah.
And there's all these triangles. And let's just look at the shadow triangles.
Yep.
And so this vertex here has 5 of the things around it.
Oh, so it's got 5 shadows. 1, 2, 3, 4, 5 shadows. Yep.
This one here, this radiation symbol, has 3, and that one has 2.
Oh, okay, so it's
5, 3, 2.
And that would work actually if you picked any triangle.
They're all 5, any 3, of them, 2. And there's all reflections to get between the light ones and the shadow ones. So on the sphere here, this is a completely regular tiling, right?
It's 5, 3, 2, and it closes up nice and neatly.
And they're all the same shape, and they're all the same size. On the wall, this is the this problem with projections is that you distort things, right? So this beautiful regular tiling on the sphere becomes
lovely spherical tiling, not so good.
It's pretty cool.
Okay, no, I'm enjoying it.
There's some really nice things about stereographic projection. Yeah. For instance, that the angles are always right. So on here, you know that they're going to be 60 degrees at the three angles.
So angles are preserved?
Angles, yes, so 60 degrees, 60, all these things here.
So you lose straight edges?
Right.
And these are all straight on here, but they're not.
You lose the lengths of, the distances of things are not correct.
Yeah.
But the angles are correct.
Because people get a bit upset, they go, this isn't a real tiling, because this is different to that.
Right.
Because it gets
Which
bigger.
is fair enough.
It's
I mean, the real tiling is
here.
here. But the other thing that's really cool is the circles here, all these edges of the triangles are great circles, and they turn into circles on here.
Oh, so they're
all of these beautiful circles.
Oh, so you can see there's like a complete circle
goes all the way around there.
And that would match to a great circle on here. So, oh, that is nice.
Yeah, it's beautiful.
And why is this on a...
Oh, yeah. So this is more interactivity. So this thing, you can slide the torch into the center. So this is no longer stereographic projection. Right. This is mnemonic projection, which is some of these are.
So let's now pull apart another name.
Whatever, yeah, I haven't looked that one up, so good plan. So the line's in the middle, and now the interesting thing is all the straight lines are straight lines.
So now straightness is preserved.
Straightness is preserved, angles are not preserved.
Oh, that's so...
Right, so here you can see like it's not really 60 degrees anymore.
So if you're a fan of straightness of lines,
yes, this is your projection.
This is your projection. If you're more of an angle kind of person,
yes, you want to be there.
You put it back on the surface of the sphere, not the center, and then
there you go.
And there's a compromise. It's terrible.
Where you have neither of the things.
Yeah, you got nothing you're after there. You know what? I am a angles, and I like great circles.
It is very pretty.
I cannot lie, and so that's
all right.
That's good.
Let's do 632.
632
going up, right?
Oh, okay, so 532, just 532. The first numbers incremented to 632.
632. So we can see on this tiling, let's see, there's a vertex. There's a vertex that has 6 of the
six of those
triangles.
Around.
And then we still have the 3
and the 2.
And the 2.
So the pointy end has one more, and those are the same.
Yeah.
Okay.
But what has changed, on the wall, you've got a beautiful, sensible tiling where all the triangles are the same size.
Whereas this is a mess.
This is a mess, yes. So, right.
So, that's great. And
732.
732.
Right. 732. So 532, beautiful on the sphere, messed up on the plane. 632, beautiful on the plane, messed up on the sphere. 732, messed up.
Messed up everywhere.
Messed up everywhere, because it's hyperbolic, right?
Right.
So there's, this is some sort of, this is your Poincare disc.
Right.
Model,
Yeah.
Your Escher pictures.
So yes.
And
so this is like an Escher tiling.
Yeah. And right, there's your 7, 3, 2 again.
Yeah.
There's another 7 here. But yeah, the triangles are getting smaller, so it's not really correct on the plane.
You've got to cram more, classic hyperbolic, you've got to cram more and more.
Yeah, I mean, you just can't do it. You can't fit all of hyperbolic space in Euclidean space. And the interactivity here is you can turn this handle. Whoop.
Oh, that's...
And you get another.
Oh, now okay, yeah.
And then this is the upper half plane model of
hyperbolic
plane. And you can, and again, the triangles are still messed up, right? They're getting smaller.
Yep.
But you can still see, your geodesics. So what are your geodesics? Your geodesics are these semicircles.
Yeah, now they're pop. And what do they become if I rotate this?
Yeah, so it's the side.
Oh, that side, sorry.
And this way, they are. There you go. They're these bits of circle.
Oh, okay. They're not semicircles, but
they're bits of circle that hit the boundary at right angles. Yeah.
Got it.
Yeah. So that's the best you can do. Yeah.
So in conclusion,
right.
632 is Euclidean.
Anything
below that is spherical.
Yes, that is correct.
Oh, okay. So you go all the way that way, spherical.
Yeah.
Where there's too much space on the plane, but it works on a sphere.
Yeah.
Anything above it is always hyperbolic.
It's hyperbolic, yeah. And then you can't do anything. Well, you can draw pictures, but you can't get...
You can't.
You can't.
So there's a sweet spot there,
yeah.
And then infinitely many, which I like it.
Yeah.
We're in the final room, which has...
the layer of the hypercube.
And a flashing button.
Right.
May I press to start?
You should do so, yes.
Right, so people come in, they hit that.
Right. So there's some audio.
Right, okay, yep.
So this is using 3 sort of ideas to show something about the hypercube. And the first is the idea of a zoetrope. So if you can
This is old school animation.
Old school, yeah, Victorian zoetrope.
Oh, look at that go.
So you got your spinning
look at that
thing, and you look through the slits.
Yeah, it's a horse running.
You see the horse, and
galloping,
and you notice that it takes all of his feet off of the ground at the same time, and you win a bet
controversial
on this.
at the time, yeah.
And there's some guy who's jumping over the thing.
So what you're trying to show here is if you've got lots of frames, physical frames moving, and you regulate when you see them.
Right. And you see them only for a little, tiny little bit at a time, so you don't get this blur.
Yeah.
It looks like a movie.
Got it.
And now we've got YouTube, we understand this.
Yeah.
Then we go over this side.
Oh.
So the second idea here is reducing the dimension of a thing, right? So here's this cube.
3D cube.
Let's make it go.
Hit it.
Yeah.
Oh.
So 3D cube, very familiar. We know what
and
cube
it spins.
is. And we see a shadow, and we're very familiar with like what this means.
Yeah, because our brains are used to 3D, so we see that.
We see that.
And we're thinking that.
And we don't know which way around it's rotating, but anyway, whatever.
Yeah.
But yeah, so we understand shadows, and we understand that gets us from 3D to 2D.
You can project down a dimension.
And so we're going to go from 4D to 3D.
To see the 4D cube.
To see the 4D cube somehow in 3D.
Love it.
And now the problem with this kind of projection, just casting a shadow, is you notice like the edges are crashing all the time, right? The edges are crossing over each other. That's going to be super confusing. If you're going from 4D
so
to 3D.
So in 4D, right, you have things passing through each other in 3D.
Yeah, so you want to avoid that.
Right.
And that's what so the next one, let's do this. So it flashes to this. Yes, we're getting back to that soon.
It's just, we'll get to you,
And then we do this. So you have to come around the side.
Oh.
Maybe you can see over here. Yeah, well.
Oh, look at this.
Will be secret. So there's this
Can we shuffle around?
Cube. Yeah, let's go around here a bit more.
Yeah, okay.
So there's this cube that's been blown up into a beach ball.
Oh, so you've just taken a cube.
Right, just gone.
And sphered it out.
Yes, radial projection.
Radial projection.
And then the point is that now it's on the sphere, we can do stereographic projection onto the wall. And stereographic projection has this wonderful property that it doesn't have any crashing, right? So, or unless one of your edges is actually at the light itself.
And so when it hits that, and then you get as if this thing's wiping around.
Yeah, well, it's sort of,
in theory, it should peel
It goes
off
around infinity.
Infinity and come in the other side.
But
okay.
And so
again, very expensive. Right.
Well, right. So for this cube, this ordinary 3D cube, you know, there's no way to avoid your edges hitting
that line.
But for the 4D cube, you can avoid it.
So you fix that problem, right? Yeah. So that's why.
Right.
That's why the whole point of the exhibition, I guess.
Right.
Stereographic projection does things that just a normal projection wouldn't do.
So this is not, this is not a one-to-one map because you get crashing.
Yep. No crashing.
It is a one-to-one map, and so let's go to this thing.
This thing is turned on. Yeah. So this is very exciting.
Let's just show it.
Let's just show it. What do I do? I guess I push the blue one.
You press the flashing blue button. Yeah. There we go.
Oh my goodness. Whoa. That's incredible.
So this is a zoetrope, right? It's got 30 frames, just like the old Victorian zoetrope, and it is spinning around.
But you've printed the frames.
We've printed the frames, so
this is the way to do 3D frames.
Right, each one, so this is the hypercube from the one back in there. And so these are all sort of rotations of that in four-dimensional space. And then take the shadow down, and you get these different shapes. And then, so what's going on here is that it's rotating around on this turntable, and there's actually magnets underneath each one of the frames.
Yep.
And there's a sensor that sees where it's coming over, and it flashes the strobe.
As it goes over.
As it goes over, very, very briefly, like 0.3% of the time or something, the light is on. And then
that looks like
there
it's
you
just
go.
hovering and moving.
Right. And so it's rotating, it's sort of doing this turning inside out thing, which is similar to the, actually we can turn this one on as well.
Okay,
so,
what's that?
So there's the beach ball cube is going at the same rate as the hypercube.
Oh, so they're synced.
They're synced up, right. So you can sort of see this.
Very pleasing.
Right, so every so often the thing goes to infinity, and at the same time there's a big thing.
As the big thing flips around the outside.
Does this jellyfishing thing.
Incredibly nice.
And so it's rotating through here, and at the same time it's rotating through this way, because you can do lots of rotations.
You're also spinning it this way just unnecessarily.
It turned out, interestingly enough, that it was very slightly easier to code up.
Really?
To make it do that as well.
Have it doing a little barrel roll at the same time.
Yeah, and it's and it's cool.
Why not? Why not?
Because so rotation is. We often think of rotation as happening around an axis.
Yeah.
But that's because we're three-dimensional.
We love our.
But really, rotation happens in a plane.
Right.
And in 4D, you have two different planes that have nothing to do with each other, so you might as well.
You may as well exploit them.
Yeah.
So just to completely break it down.
Right.
If you start with a 4D cube and you radially project it out onto a false 3-sphere?
The sphere in 4-dimensional space, also known as the 3-sphere.
Confusingly.
Or the hypersphere.
The hypersphere, okay. So if you radially project it onto a hypersphere, and then you stereographically project that down into 3D, while rotating the hypersphere it's on,
indeed,
you get this.
You get these different shadows, and then
you've animated them physically.
Right. Yeah.
That is deeply pleasing.
Yeah.
It's been great visiting Brilliant Geometry, the exhibition. If you want any of these things, this is partly supported by Shapeways, and these are available 3D print on demand. And so I'll put a link to Henry Segerman's Shapeways page in the description. You can order the vast majority of these. You've got to provide your own torch, but you can get the 3D printing done. The principal, main sponsor of this is the University of Warwick, and so we're hugely grateful to them. Without them, I mean, this just wouldn't be happening. So thank you so much, University of Warwick. And of course, University of Edinburgh has been involved because it's in their backyard. The summer hall have been amazing. If you want to find out more about the ridiculous spinning, flashing LED extravaganza, I'll have a link to Peter Reed, who's the guy who built it, in the description below. Though, fun fact, the people who have actually paid for this video, my fine Patreon people, I've done some bonus filming with Henry and Peter where we look under the hood of the spinning thing and how it all works. So if you do help fund these videos, which is what makes it all possible, on Patreon I'll have a link to that bonus footage where we go behind the scenes. But yeah, a final thank you to everyone who made this possible, and yeah, links below, check it out.